Start the next talk. So the next pedagogical lecture is going to be by Maxime Colin, who works as a researcher at Libin Center for Tropical Marine Research in Germany. So he's traveled all the way from Germany to give this lecture. Following up from radiation, we'll hear more pedagogical stuff on convection. So let Maxime discuss broad questions in this area and set the tone for the following discussions.
Okay, so thank you for introducing me. So my name is Maxime Colin. I come from France, and I now work in Germany as a postdoc in this center here. It's called Leibniz Center for Tropical Marine Research. I work with Professor Jan Herter there. And I did my PhD a few years ago with Stephen Sherwood and Sandrine Bonny, and we were working on convection. So I'm very happy that I have the honor to give you this introductory lecture on convection. There's many people who know a lot about convection here, so feel free to just jump in and add some comments if you see anything interesting. I picked this photo here, which a friend of mine took this photo. I think it's the perfect one. And this is, you can see it's raining, and the cloud is, I don't know, it's not very deep, right? I would say it's a congested cloud. It's not a very deep cloud, but still raining a lot, which is very nice. But let's try to explain some of these things about convection, maybe step by step. So the first thing to ask is, what is convection? Do you have some answers for me? What do you think if you had to answer this question in simple terms? Yeah, I think that's right. I think you said movement of fluids, yes? Yes, I like that. Yeah, that sounds very good. I think the point I want to make here is that many debates in science are there because people don't agree on the definition of things. And that's why I think it's always important as scientists that we define the things we are talking about carefully. It's true in a lecture, it's also true in research. We have to be precise so that we have... Sorry? Uh-huh. Interesting, yeah, okay. This relates to the previous lecture, yeah, we talked about the energy transfers. So you said vertical advection, yeah, so this is an interesting way to define that, yeah. Do you have any other things to add in this sort of conceptual picture that we are trying to build? So energy transfer, some vertical advection, some movement, you said, yeah? I think this is all kind of right. And if I try to summarize these things, so in physics, one of the definitions you can have is that it's the general motion of a fluid due to the collective effect of all the movements of its molecules. So this relates a little bit to the energy transfer definition that was introduced in the previous lecture and that you mentioned. And I think the idea here is that it's not diffusion. Right? It's not the diffusion of the particles or of the molecule, it's something collective. But actually, I don't like this definition, it's not precise enough. So in thermodynamics, there's a more specific definition, perhaps, is that it's the general motion of a fluid due to a gradient of temperature or a gradient of other properties of the fluid. Right, so you have the idea of motion that you mentioned, and there's the gradient of some properties of the fluid. I think this is nice for us in climate science, that we can think about it as the general motion and it's related to a gradient. But when I was doing my PhD, I once went to a talk by a mathematician. He was talking about horizontal convection. Oh, I found, oh man, what is horizontal convection? That doesn't make sense. But with this definition, yeah, it's possible. You have a horizontal convection. But that's not what I want to talk about today, right? So let's have another definition, which is more suitable for perhaps meteorology. It's the vertical motion of air, usually associated with gradients of density or temperature. I think this is something that makes me happy, but the others are also fine, right? You need to decide what you talk about. I think there's something implicit here that nobody writes it in the definition of convection, is that something is relatively fast. Right? This is the idea. It's just any vertical motion of air, would we call it convection? Right? It's relatively fast. If it's just slowly going up, for example, near the top of the troposphere, in the tropopause, the air is going slowly up. Is that really In convection, maybe not. Anyway, so let's stick to that. And to have a picture in mind, convection here includes the dry convection, so just movement without any cloud formation. We have this in the boundary layer all the time. We can also have it in the free troposphere. There's shallow convection, so shallow clouds. Probably that means clouds that are not too big, that they tend not to have a big transfer of energy towards the high troposphere. And there's the deep convection that will go all the way up to the tropopause. I think when we think about convection, we have to keep in mind that there's a huge spectrum of temporal and spatial scales that are involved in convection. So I guess I like to think about it at the scale of a few kilometers and maybe half an hour for just a cumulonimbus, maybe an hour. Okay, this is just the pure convection, but actually it can grow to mesoscale convective systems that would be several hundreds of kilometers and could live for a few days. And then you can even grow it further, like synoptic cluster or tropical cyclones that would last for many days and be as large as 1,000 kilometers. But still, it can also be included in planetary scales like the Madden-Julian oscillation, tens of thousands of kilometers and lasting for weeks. So I think convection has this interesting thing that it's sort of impacting all the scales at the same time, not just the spatial scales, but also the temporal scales. We have to keep these two things in mind. And when I think about convection, I can only think about clouds, right? We are lucky in convection that not always, but sometimes we can visualize it with the clouds, right? So we have cumulus clouds here. This is a very nice cloud field, so very shallow. We have a deep cloud here. It's starting to form an anvil here. And you can see this, I don't know, I'll call it a cumulonimbus, but yeah, it actually, there's a jungle of other clouds around this, right? It's not just one cumulonimbus like this. There's like a family of clouds with it. They work collaboratively. There's this thing which maybe we call congestus, not too shallow, not too deep. There is precipitation, right? So it's nice to think that shallow doesn't precipitate. Yeah, it makes it very clear to define it. No precipitation means shallow. Sometimes people say shallow can precipitate, so you have to be a bit flexible. That's why congestus solves this problem. Yeah, it's precipitating, but it's not deep. And you have this thing which is, you know, maybe a spatial organization of many different deep clouds together. They start to form some anvils. There's various layers. So yeah, this is all convection. Okay, that's the most important thing. Now, what causes convection? Do you have some hints for me? Vertical gradient of temperature. Yeah, that sounds good. Yeah, good, very good idea. Yeah. Other ideas? Instability, yeah, instability buildup. Moistening and temperature buildup. Yeah, okay. You're doing this with your hand, that means low, right? You're sort of doing low there. There's some temperature buildup, some moisture building up near the surface. Yeah, sounds good. Other things? Dynamical convergence. Okay, so I suppose then this was thermodynamic, right? This was more of a dynamical thing. So convergence of air has to go somewhere. So maybe vertically, yes. Okay. Contrast between land and ocean, that could be related to that. Maybe the contrast would then create some dynamical features that could lead to convection. Yeah, yeah. I think that's all good for me. We have to start somewhere. So let's start step by step. Let's just take a parcel of air somewhere. It has a temperature T, a density rho, and a pressure P. Let's assume it's still. Right? So we are in a stratified flow, it's not moving. I'm going to force it to move upwards with a certain displacement dx. And the question is, what happens then? Well, it's a bit higher. It has a temperature T plus dt. It has a density rho plus d rho. And then I'm going to ask, okay, what's going to happen to this parcel of air? Is it going to convect or is it not going to convect? Well, then I have to sort of take into account what's on the sides, right? So let's call it the environment. So if this parcel of air is warmer, or maybe lighter, it will go up. If it's colder, or if it's denser, it will go back down to the original level. So I think to manage to have convection, we have to have something warmer or lighter that it's able to, if I push it up a little bit, it will then naturally go up. Yeah? So I think this is the idea of instability. We can try to write that down with equations. So I think we have understood the process a little bit, but with equations, let's try to do it nicely. So we have this parcel. I changed the bubble to a cube because it's nicer to write equations on cubes. So here we go. So we have a parcel. Tp is the temperature, rho p the density, pp the pressure. And we have the environment, T rho p of the environment. Let's move it a little bit by a certain displacement dz. And we have new properties, Tp plus dTp, etc. And we have a new environment, T environment plus dt environment, and etc. And we have to compare these two. So to compare these two, what I would like to do is I would like to know what sort of forces are going to act on that parcel, on that little cube of air. So what sort of forces should I consider? What do you think? What's the first force to consider? Pressure, yes. Gravity, yes. Friction, yes. Already good, yeah? It's a good start. Yeah, we can probably think about other things, but I think it's nice to just think about the major one. So let's do with that. Yeah, what are the forces? So we have gravity, yeah, and we have the pressure. The pressure at the level z from below, and the pressure at the level z plus dz from above, yeah. And let's try to write this, keeping in mind that we have this final picture. Maybe it's going to go up, maybe it's going to go down. Okay, let's start to make some assumptions now to carry on. You can see that I didn't include the friction in this picture. Yeah, we can include it, but just to keep as simple as possible, let's neglect the friction. The environmental air, let's assume it's going to be in hydrostatic equilibrium. Stop moving, everything is still, so I will just assume hydrostatic equilibrium for the environment. So dP dz is minus rho g for the environment. There's a nice thing also that's easy to assume. It's not very costly. We can just assume that the pressure is instantly equilibrated. The pressure of the parcel is the same as the pressure of the environment very quickly. If we don't want to include that approximation, then we have shock waves. This is not really climate science, right? So let's just assume the equilibrium is there. And we can write Newton's second law on the parcel. So this is the acceleration. This is the gravity. And these are the first pressure from the bottom and pressure from the top, right? On the sides, doesn't matter, it's balanced. So if you put that together, this P environment of Z and P environment of Z plus dZ, you have the derivative that appears here. And so you can put that together to have the acceleration, d2Z dt2 is the gravity and the pressure force. Very simple. Okay, this is equation 2. Now if you put 1 and 2 together, then you can get the acceleration of that parcel of air. It's just the difference between the density of the environment and the density of the parcel. Pretty good. This is what we were kind of saying, that if it's lighter or denser, it's going to go up and down. It appears here very quickly in just 2 lines. Density is good, but we like to think about pressure, about temperature, sorry. It's just easier. So if you use the ideal gas law, you can just rewrite this in terms of difference of temperature. So that's why I put it red and blue, because we like to think about temperature. This thing is called buoyancy. Yeah, buoyancy is the acceleration of that parcel. So it's just the buoyancy due to this difference between the parcel and the environment. So buoyancy as the units of an acceleration. So I keep this equation here that we just saw. The acceleration of that parcel is the buoyancy. Now let's introduce a few things to go a bit further to try to explain this Tp minus Tm. How can we just make it even more direct? So let's use potential temperature. This is the definition of potential temperature. And if you calculate the derivative, sort of the logarithmic derivative of this, you have depends on the variation of temperature and the variation of pressure. You do this for the environment, and you also do this for the parcel. And the beauty of it is that this parcel is going to conserve its potential temperature. So this is 0. And if you consider the small changes of temperature for this thing, so the temperature of the environment at Z plus dZ, once I have displaced it, it's just the temperature of the start plus a little change. You can do the same for the parcel. Temperature of the parcel at Z plus dZ is the temperature of the start plus a little difference, dTp. Right? So you have two differences, the dTp and the dT environment. What you want to know is the difference between these two. You've got Tp minus T environment. So we try to put this together. The beautiful thing is that we started from this place, which is in equilibrium. So the T start is the same for the two, and the environment and the parcel. So if we then put together these two things, we can see that the temperature difference is just the difference of these tiny variations. And these tiny variations, this difference, you can get it by rewriting these two equations on the theta of the environment and the theta of the parcel. If you put that together, okay, we can just get this in terms of the variation of the potential temperature of the environment. I can let you do this peacefully, you can just do this calculus peacefully later. So the acceleration of that parcel is the buoyancy, and you can just rewrite it as the potential temperature, the variation of potential temperature of the environment. So it's very nice and simple. These things look a little bit ugly, but finally we have a very simple equation. So this thing we're going to call it n squared. It's a definition. We call it n squared, g divided by theta environment, and then the derivative of the theta environment. This is called the Brunt-Väisälä frequency. Right? It's just almost the same as the derivative of potential temperature. Okay, so that's what we have. If I summarize, we have the acceleration of the parcel is the buoyancy, and it's minus n squared dz, and this is the definition of n squared. If the derivative of the environment, of the potential temperature of the environment is positive, then we have a frequency which is real, and so we have oscillations with frequency n. So if I would displace the parcel a little bit, it will go back down and it will just oscillate very gently. So this is stable, and we have no convection. If we have the derivative of the potential temperature of the environment, which is negative, it means that n is an imaginary number. And so you have the z here of the parcel, something that will grow to infinity. It's an exponential growth, and so it's unstable, and so you have convection. So I think the idea is very simple, and this is probably what you said. Convection occurs when the atmosphere is unstable. Whatever you say, maybe it's the variation of temperature, or you just said it's unstable, this is all good. So it's very easy to write it down just with Newton's second law. We can always rewrite this way. And so the Brunt-Väisälä frequency is kind of the ally to understand this. Okay, so to summarize then, how will this go? So this was a very small step, and I'll do a small displacement and I look at what's going to happen. If we integrate it over the whole life of a potential cloud, well, we have some bubble of air which is warm and humid, right? It will go up because it's maybe warmer and lighter, less dense. And the pressure decreases when we go up. And so as a consequence of that, the temperature decreases because it's an adiabatic expansion. So when the pressure decreases, the temperature also decreases. And at some point we reach saturation where the air reaches the maximum amount of water vapor it can contain. You have the cloud base there. And then the excess of water vapor will condense. Right? This is a fairly simple thing. You can just explain this with just simple ideas. There's an interesting thing that the cloud droplets can become bigger and eventually become raindrops. So what do you think is a cloud droplet and what do you think is a raindrop? What's the difference between these two? Yeah, the size is different. Yeah, exactly. So it's the same thing, obviously, in terms of physics. What's the size of a cloud droplet and what's the size of a raindrop, typically? Yeah, micrometers. Yes, this is micrometers for the cloud droplet. Yeah, yes. Exactly. So the raindrops might be 1 millimeter, 2 millimeters. So it's 1,000 times more. Yeah. So the cloud droplets, they fall very, 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 very slowly. It's very sticky for them. But the raindrops, they fall very easily. So the Reynolds number, it's very high for the raindrops, but not for the cloud droplets. Okay. So let's try to have convective instability put on a proper diagram. So here we have a parcel here, and we have a certain environment, which is this solid line here, and the temperature goes down when you go up, right? And then what you have to compare it with is with the adiabatic change of temperature along this dashed line. So if you bring that parcel up, it is colder than environment, so it will come back down. So this is a stable case. The stable case is when the gamma prime, the lapse rate of that parcel, is larger than the lapse rate of the environment. If they're the same, it's neutral, and if you have a larger lapse rate in the environment, then it's going to be unstable and you have convection. So we did it with the Newton's law, and you can also just directly see that by comparing the profiles, by comparing the lapse rates. So here's a typical environmental lapse rate that you can find, maybe 6.5 Kelvin per kilometers. And you can have a dry adiabatic lapse rate. Well, you can calculate it. This is about 10 Kelvin per kilometers. And you can also have a moist adiabatic lapse rate when you are conserving equivalent potential temperature. We'll come back to that. And this is, it depends, right? The value depends on many things about the context, but it can be typically about 4 Kelvin per kilometer, you know, near the ground, for example, when it's quite moist. So you can see that typically the environmental lapse rate is in between the dry and the moist adiabatic lapse rate. So it would be stable for an adiabatic, for a dry adiabatic displacement of air. It will tend to come back down. But it will be unstable if it's following a moist adiabatic, if it's in a saturated mode. If this parcel of air becomes saturated, it becomes unstable. So this is what we call the convective instability, conditional instability, sorry, conditional instability. So in all that area in between a dry adiabat and here a saturated moist adiabat, in all that area, it is conditionally stable. It depends if the parcel is already saturated or not. So I think this is just maybe to clarify the conditional instability. This is what is causing convection, just directly. When we have a saturated parcel, the conserved variable is the equivalent potential temperature. And when it's not saturated, we just go back to potential temperature, which I have used without defining very, very clearly, but just to save time. Do you know how to find the equivalent potential temperature? Do you know how to rederive this? Typically, it's done by using the entropy of that parcel. So usually people write the entropy S, and they say, okay, we have dry air, we have water vapor, we have some liquid. You could have ice, but let's not take it. It just makes things more complicated. And then you say, okay, it's going to be conserved for a reversible adiabatic transformation of that air. And so you have to write these 3 different entropies, right? For dry air, for the vapor, and for the liquid. This is done by just basic physics, ideal gas, and for liquid, like a perfect liquid, let's say. And if you use these definitions, you can write these beautiful equations, but it takes time, so we're not going to do it now. And you can write the definition of equivalent potential temperature. So it's conserved. Beautiful, we have a conserved variable. We like it in physics to have conserved variables. That's fantastic. Okay, so what causes convection is the convective instability, right? This is my very easy step. Now, what's causing convective instability? I'm going one step further. I think you have already mentioned some of these options, right? So let's try to go through this. The first option to create convective instability is to have a warm and humid parcel of air, let's say near the surface, and you want this thing to be buoyant so that it's going to go up. So just to be buoyant, it can just be warm, but you can also be humid. And what's the simple reason for that? It's because the water vapor molecule is lighter than any molecule that is dry, so N2 and O2. And so because of that, it makes the air lighter. So it gives a small advantage if you're a humid parcel. It gives a small advantage in terms of buoyancy. It also gives a big advantage as soon as you saturate, because then you can actually release the latent heat. It also gives a small advantage when you are not saturated yet. So this is called the virtual temperature. Do you know how to derive this virtual temperature? It's not that complicated, so I think we can do this. I think we have to remember the ideal gas law. P is rho RT. And we have to say that, okay, the actual pressure in the air is the partial pressure of dry air, whatever that means, N2 plus O2, plus the partial pressure of water vapor. You can just sum them up. That's beautiful. And then you can use the ideal gas law here. You have the rho dry, the gas constant for dry air, and the temperature. And you can write the rho of water vapor, the gas constant of water vapor, of water, and then the temperature. And then at the end, we want to say, okay, well, there's water vapor and there's dry air, but what if it was all dry? So at the end, you want to put that together and have some rho R dt. So you want to factorize by rho R dt. So if I want to factorize by rho R dt, here I have a rho d divided by rho, and here I have a rho v RV divided by rho RD. Now you have several solutions. First thing is the lazy solution, the easy solution. Rho d divided by rho, what is it? It's called the specific humidity. It's the definition, specific humidity. So it's going to be QV. I'll write it QV, specific humidity. And here you have 1 divided by epsilon QV. No, this is Q dry. Q dry is, yeah, I should have written that before. It's going to be 1 minus QV. And then you can factorize this, blah, blah, blah. And then you can have rho R dt. And then you have 1 plus 1 divided by epsilon minus 1 QV. And this thing here is the virtual temperature. So this is written with QV, which is specific humidity. But actually, if you look at the equations, we don't usually use QV. We use the mixing ratio of water vapor. So RV is not the same as the specific humidity, right? What is RV? It's rho d divided by rho dry for dry air. What is QV? It's rho v divided by rho total. And so it's not exactly the definition there. So you have one other lazy solution to say, yeah, they are different, but they're not very different. They're about the same, yeah? So you can then go back to the full definition. But if you want to make a proper derivation, then you can actually go back to this, and you can write, okay, here I have rho d, rho v, rho. Then you can go back to, okay, I just want to keep the division by rho d. So I'm not going to do it, but let's say as soon as you see rho v divided by rho, you're going to say, okay, I multiply by rho d divided by rho d. It's painless to multiply by 1, it's fine. And here you have the mixing ratio. And if you do that clearly, then you can actually have the pure, the serious definition of virtual temperature. But I'm not going to do it today. Yeah. Just to do a bit of calculus, right? To warm up a little bit for this week. So you can practice a little bit these things, and you can do it cleanly. You can also do the lazy way, right? It's good to do the lazy way first, and then let's do it cleanly to make sure we understand what's going on. So, okay, virtual temperature, it takes into account the fact that when you have water vapor in the air, it's a bit lighter. But there's another one, which is called density temperature, and it's even more precise, because in the density temperature, you take into account the fact that, yes, the water vapor makes the air sort of lighter, but you have the liquid like droplets, and you have the ice, and they make the whole thing denser or heavier. And so they sort of reduce that ability to be lighter or less dense, right? So you can actually also do a proper derivation, without making any assumptions like the lazy ones, and you can actually show that the density temperature is this. Okay, so usually we like to think about convective instability with a lovely diagram, which is a skew T-log-P diagram. So I'm not going to try to explain all this, take some time, so yeah, I'll go quickly, but I'm sure you know about these things. So, you have a parcel, here's this temperature, here's this, dew point temperature, and so when this parcel is going up, it will follow a dry adiabat. So it would cool down very quickly. At some point, it will become saturated, like here, and then it will continue to go up, but on a moist adiabat because it's releasing latent heat. And so as soon as you have this point here where the temperature of the parcel and the temperature of the environment are the same, it just convects freely, right? It's the level of free convection. And this is how you define the cape here. So if you want to create convective instability, what can you do? Well, one option is that you want to warm up that parcel here. If you warm it up by whatever mechanism, maybe radiation, maybe some land ocean, structure, you can try to do that. And you can just also be by luck, right? Let's say by like sort of pseudo-random things, and then you can be a little bit warmer. So that's a good mechanism in the day. In the day, you often have this. Okay, it's warming up in some places. It will be easier then to have convection. So one example for this is a tropical island. So if you take a tropical island, which is a very, very simple island, a small island, let's say, small island here, then you have ocean on the sides. Well, the soil here has a pretty low heat capacity compared to the ocean, which is water. And so the soil will warm up faster with the sunshine in the day. And so just above the island, the air is warm and probably also a little bit humid. So it can be less dense, it rises, it creates a sea breeze, right? When you have that, it creates a sea breeze. And so this sea breeze is reinforcing, right? You were mentioning that you have, advection from the sides or let's say dynamical features that can create convergence, which is the case here. And this convergence in the island case is reinforcing the formation of clouds, yeah? So it reinforces the rising movement. And so with this example, what's the conclusion? It creates clouds just above the island. Islands enhance cloud formation, yeah? I tested this thing, yeah, with my eyes. And this is a picture right here. You have a small island and you have clouds just over it. It works very nicely. And I didn't have to work very hard. Every day was about the same for this particular island. Not all every day, sometimes it fails. But very often you have this picture. So it seems to work fine, this explanation. Okay, there's another option to create convective instability, and it's the radiative cooling in the free troposphere. So what happens if we have radiative cooling in the free troposphere? You kind of have you have this diagram, okay, you have this area, this is the parcel, this is the environment. But if you have radiative cooling, it's going to bring that environmental condition to colder temperature. It means higher cape. It means, yes, it's much easier to have convection. And so this is a good mechanism at night, especially over the ocean, right? It's pretty good to create convection like this, just by radiative cooling of the free troposphere. Yeah? This is also another way you can just create convective instability. So one was the warm air at the bottom, another one is the radiation sort of at upper in the air. There's many other options, right? But I'm just going to mention one last one, which is the mechanical lifting, for example, by topography. So if you have a mountain and you have maybe the wind is pushing this air here to go up, well, the air has no choice. It has to go up. At some point, it will saturate. It will create a cloud, even if it was not particularly unstable, but still it can create a cloud. And then after creating a cloud, okay, the air comes back down much drier and much warmer because it's going to have a, adiabatic compression. You have warmer air on the other side of the mountain. This is also very simple phenomenon that you can observe. So yes, if you have here, mechanical lifting, well, you can just go past the sin, and you can just directly start from upper in the air where it's already buoyant. Yeah, this is another possibility. There's many others, but yeah, I'll just stop here. Okay. Can we imagine a world without convection? It would be sad, but yeah, it's possible to imagine a world without convection. Yeah, it's just a radiation lecture. And yeah, we can imagine that. Some people have done that. They got the Nobel Prize for it, so it's good to just think about crazy world. So, here's the temperature as a function of pressure. And if you are just with radiation, no convection, well, you have this very steep lapse rate. It's getting very, very cold quickly in a radiation world. But if you actually take into account convection, well, it is not cooling up as fast when you go up. So if you have pure radiative equilibrium, the lapse rate is very high. It's very cold up in the air. This is very unstable, right? It's unstable for convection. So very quickly, convection will come up and say, no, it will put it back to an adiabat, or approximately an adiabat. So a world without convection is an unstable world, of course, for convection. So yeah, I think that's what it was written here. So this is the famous diagram, the one that everybody shows. Yeah, this is this famous paper in 1964. And it works very well, right? As you can see, it's getting really cold there. Convection will put it back to the dry adiabat. Well, actually, Manabe had a correction on this paper. It's this one. And actually, if you have a world, this is this line here, the world with no convection, just radiation, it is very, very steep, the lapse rate, but only over a very small period. And then as soon as you're a little bit up in the sky, it's not very, the lapse rate is not very high anymore. So it will still be true that if you have a world with radiation only, it's very unstable, but just during the first kilometers, then it's a different story. To make all of this, you have to make some assumptions, right, to get these things. So yeah, Manabe changed the assumptions and showed, yeah, it's a little bit sensitive to that. But the main idea is the same. A world without convection, obviously, is unstable to convection. Convection is there to put it back to a stable profile. Okay, an order of magnitude. Let's give an order of magnitude for convection. Here is one conservation equation for S, which is dry static energy. The bar sort of means the vertical integration, vertical average, but let's say vertical integration. And so if you write this, you can see that there is here convergence. Here you have radiation. Here you have the condensation, condensing everywhere where you have the cloud. And here's the sensible heat flux at the surface. In a nice world, everything is stable. There's no change of energy. Well, you can just say this is about zero, this is about zero, and you have a simple balance between the three important terms: radiation, condensation, and the latent heat at the surface. In practice, the latent heat at the surface is much smaller. Yeah, so I can even go one step further and say, okay, the condensation in the air is balancing the radiation, approximately. Yeah, actually, this one is not completely zero, but. And so if you do this, you can see that yes, there is radiation. It's doing one thing, but it's balanced by convection, which is doing the other thing. So I think people call this the radiative convective equilibrium. Yes? Radiation is doing something in one direction. Convection is putting it back in the other direction. If you put in numbers, they have done it in this paper. If you put in the numbers, then you can see that actually a cooling of about 1 Kelvin per day, which would happen on the planet, is a means precipitation of about 3 millimeters per day. Right? So that's the order of magnitude for radiative convective equilibrium. This is for the tropics. Okay. In the next part, I want to just briefly go through a few characteristics of convection and to talk about some convective structures. I guess the idea is we have to try to sort of picture what sort of objects are there in a convection. When you think about convection, what sort of object do I have in mind? Yeah, is it like a column of air going up? Is it like a more unsteady thing where things are moving? It's turbulent. Yeah, so these are all things that we have to think about. So what you have is updraft, right? Usually people think about convection as having updraft. Air is going up, creating clouds, and then going back down, It's a downdraft. The downdraft, usually occurs when it's raining, because if it's raining, the rain can evaporate. So it's cooling down. So it's producing dense air. It's going to fall to the surface. And so you have a downdraft here. Often in models, you also think about, okay, do you have entrainment of air from the environment into the cloud, and you have detrainment. Some air is leaving the cloud on the sides. You can also make it a little bit more complicated, a bit more objects, right? When you have the downdraft here with precipitation, you create a cold pool, right, in this cold outflow. You get a cold pool. You also have a stratiform part. We can't see it here. I chose this picture on purpose because you can't see it. But actually, it's also a stratiform part, and in some cases can be important. And you can also form an anvil. Right? So this is all sort of convective, part of the convective structure, yeah? All these objects. But, philosophical question, what is the real basic convective entity? Right? This is not an easy question. I think people are still trying to find out what is the real basic convective entity. Not so sure, but we can have some ideas. We can have some hypotheses. Could it be a thermal? What is a thermal? What is a thermal? It's some sort of draft of air, which is going from sort of bottom to up. Maybe I don't know. I want to picture it by being wider near the surface, because the air is converging there. It's going to be, slimmer at some point and then becoming wider again because of expansion. When the air is going up, it's expanding. So this is like a thermal, yeah. Maybe a cloud, maybe a cloud is a thermal, It's possible. Thermal is part of the story. But you can also think about it in terms of bubble. People like to think also that this thing is not actually a thermal, it's a bubble. Let's go one step before. When you see these pictures, these are boundary layer rolls. Right? The air is moving in the boundary layer. You can sort of see this thing here. It very much looks like a thermal in the picture before, right? It's wider here, wider there, thinner in the middle. Okay, yeah, here you go. You have a thermal. Maybe this is the basic convective entity. But maybe it's just a bubble. Maybe it's just a bubble. The air is moving up quite fast in the center, sort of going down on the sides, yeah? It's going up and going down. It's like a bubble. These two pictures are not exactly the same. Right? They have a different vision. And I think it's important to sort of decide what sort of vision we are doing when we want to just write equations. It's going to be important at the end. Maybe it's also a bubble like this. This is like a bubble, but just in a cloud. The air is going up. There's like a toroidal structure, right? A toroidal movement of the air, like this. And maybe it's a plume. I don't know. People talk about a plume. The plume is sort of the same as a thermal. For me, I would say that the plume is the same as the thermal, but it's bigger. It's going to go from the surface up to quite high in the air. And people talk about a plume. And in the end, are we talking about an updraft? Right? So I think all these three things are trying to be a picture of an updraft. Right? So either it's a thermal, a small thing that is going from a lower level to an upper level. A bigger one is the plume, like stretching all the way to the tropical poles, or it's just a very small bubble. And what I wanted to show here also, perhaps to give you some intuition, with some videos. I don't know if it's going to work. Okay. Let's try to build some intuition. When you see these sort of clouds forming up, this is fairly shallow. Now it's getting a bit deeper. You can sort of see the bubble. I think you can see the bubble in that. It feels like a bubble. It has these sort of motions up and down. But sometimes here it's getting quite large. It's getting quite large. It almost feels like it is a plume of air going from the bottom up to the top of the cloud. So the plume idea is not stupid either. It seems like it's also possible to see a plume sometimes. You can see it's starting to form the anvil here. I think now it's raining. So we must have a cold pool. Yeah, I think so. I think all these possibilities are probably approximately fine. They bring something to the picture. And maybe the truth is somewhere in between, right? It's a little bit of a plume, a little bit of a thermal, a little bit of a bubble. I also like this one. Is it working? Yes. I also like this one. Somehow it's taken from a wider angle, I feel. It's a bigger cloud. I like this one here. You can see that it's not, is it still a bubble? Do you think a bubble would apply to this particular part? And you look at this thing, it's just falling down completely. It's completely falling apart. It was an overshoot, right? It was just an overshoot going back down. You can sort of see it's going down. So is it a downdraft? It's going down, right? It's a downdraft, even though it was created just from buoyancy, not from evaporation of rain. We could watch this once for a little while, yeah. Okay. So another thing is the corpel. I think I mentioned it, and I think the corpel is a very simple one. It's the downdraft, which has to evaporate somewhere out of this cloud. This is a pretty bad picture because the rain is in the cloud only, so it cannot really evaporate, but it has to evaporate somewhere, and then you have some cold air that falls and splits at the surface. And this is the corpel. So I think we've talked about all of this. If I try to summarize all this sort of hand-wavy discussion about convective structures, we have updrafts, downdrafts, entrainment, detrainment. And with all of this, you can sort of build a cloud model. Actually, I don't like cloud model. I prefer plume model because then we know we're not trying to count really that, the hydrometeors or the condensate as a cloud model actually does, but it's more a plume model for convection. We are trying to describe convection, not the changes in the microphysics or how this is going to impact radiation. So all these things actually, you could sort of ask to summarize, you could ask the question how convection varies with height. This is the plume model. You have to say, okay, how convection varies with height. Is it getting intense in some particular areas and less intense at other altitudes? But you also have the intensity of convection, so how much air goes up. So I think when you think about the intensity of convection, you think about the mass flux, yeah? How much mass flux you have. And this is what people call the closure. So this is how convection varies with time. So these two things, they can be different. And yeah, I think that's it. So here on this slide, I'm trying to relate the objects that you can define just by looking at convection and the objects that you have when you make a model for convection, which is always different. If you make a model, you have to simplify all these structures like the bubble or some other, you have to make some assumptions to make it possible to have an equation and then use it in a model. So here, I'm trying to relate these two things. Okay, now let's go for a few minutes on the models of convection. Parameterizations are a model, but they are not the only models. You can also write a model which is not a parameterization. And I think I'm going to try to reduce this to just the parameterization. A parameterization is a model that you want to use to apply in another model, right? I think so the purpose of it is different because you want it to make it part of a larger model. So what's the goal of a convective parameterization? Arakawa said the cumulus parameterization problem may be defined as the problem of formulating the statistical effects of moist convection to obtain a closed system for predicting weather and climate. Again, it is an attempt to formulate the statistical effects of cumulus convection without predicting each individual cloud. So I think that's the difficult thing about convection is that I like the bubbles, but if you want to make a model out of the bubbles, it's difficult, yeah? It's difficult. So you kind of have two ways of exploring convection. One is by the models, by the parameterization, and one is by describing the complexity of the convective structure. And so this is the wisdom of Arakawa, but nowadays with increasing spatial and temporal resolution in models, does that still apply? I think increasingly the convective parameterizations are pushed to do things so that they are trying to predict not each individual cloud, but almost just groups of individual clouds. It's not exactly just doing the pure statistics. And so what is a good parameterization? Let's say, what should it do to help the parent model? It should give you some source terms for the dynamics. So warming, drying, and momentum transport. This is what you should do. You want to couple it with the big model. It should give you information about the hydrometeors to provide to the cloud scheme so that you can compute cloud cover. This is for radiation. It has to give you precipitation, because this is what we worry about, precipitation. And it probably has to give the vertical profile of mass flux. So over the years, people have come up with many different parameterizations, and this is not a lecture about parameterization, so I just have to summarize in very quick words. One school of thought was to think about moisture convergence. I think we've heard this probably before, I think. So moisture convergence, let's say that the reference paper is this one, quote 1965. The idea is that convection is controlled by low-level, large-scale moisture convergence. It's nice, it's simple, the concept is simple, it makes sense. It's based on a moisture budget. It was actually designed for tropical cyclone at the beginning, and there's no explicit representation of convective processes, which makes us sad, right? It makes us sad. We would like to represent the convection. So it's just a budget. Some people criticize this because they don't like the moisture budget idea. They would like to see an energy budget, because the energy is really the thing that controls, right? The moisture budget has to be closed, but can it really be the cause of convection? Another school of thought for convective models is the adjustment school. So we have Madhava, Strickler, Betts, and Miller, for example. In this thing, you just say, okay, there's an unstable profile that was created, probably because of radiation, but maybe other things too. And this unstable profile is going to be put back to a reference or to a target, which is approximately an adiabat, but could be different. And you could choose a target that is a little bit different. And so you actually just relax, whatever temperature you have and whatever moisture you have to the reference with a certain time scale, tau. Very simple model. So it's very effective, and it's doing fine. But again, there's no explicit representation of the convective processes, which makes us sad. It's hard to add the complexity that we can think about in convection. And so that's why now most of the convective parameterization that are used in climate models are mass flux parameterizations in the big family of mass flux parameterization. And the idea is usually based on a steady state plume concept. So you have many things now. We've described them: updraft, downdraft, cold pools, whatever. In the end, you just describe it with mass fluxes. Okay, let's try to do, in 2 minutes, a mass flux parameterization. So you have to write the dry static energy and the moisture by splitting the grid into two parts. One grid which is doing approximately nothing, and one grid which is the updraft. Right? So it's just a tiny bit of my grid is doing the updraft, sigma u, and the rest is doing compensating subsidence, slowly going down. And you have vertical velocities here. And you actually do like an average between this small part, which is the updraft, and compensating subsidence to write any quantity in the box. Any quantity is going to be an average. And you do some hypotheses, right? We neglect the structures. Okay, the updraft, can you really see the bubble in that? No, right? There's no bubble, it's just a plume. And so we neglect the heterogeneities. Okay, let's assume that the updraft area fraction is small. Sigma u is very small, much smaller than 1. And there's a slow motion in the environment. Omega u is much larger than WU is much larger than WE. And you can write the updraft mass flux. This is just a definition. Mass flux is rho sigma W. And then if you write that, you can express this effect of convection, bringing whatever quantity psi up in the air, whatever effect it is from this convective W, you can just write it with the mass flux and the property of the updraft. So that's very nice. It solves the problem of complex convection. You can just write it by knowing the mass flux and knowing the property of the updraft. But you have to assume a small updraft area fraction, which is a problem in modern models. This is not really getting true. And the slow motion of the environment, maybe this is okay, but it depends again. You can keep doing refining the model of entrainment and detrainment. You do some budgets for the mass, the energy, and the moisture, and you can just write equations where whatever appears is just entrainment, detrainment, mass flux, and the property of the updraft. You can have also a downdraft if you want. You can just add a downdraft. It's just another column here, and you just have to sum over updraft and downdraft for whatever quantity you are writing. But in the end, what you really have to do is find the mass flux and find the property of the updraft. What is finding the mass flux? Is the closure. Finding the mass flux is the closure. Finding the intensity of convection. What is the property of the updraft? Well, it is having a plume model, how things vary on the vertical axis. Right? So typically, in the convective parameterizations, you have three separate components. You have the triggering. Okay, do I activate convection or not? Is there actually deep convection going on right now? And then you have the cloud model, the plume model, I prefer plume model, how things vary on the vertical axis. And then you have the closure, how things vary in time. So it's about the intensity. I think this is bringing me to, bring me to the end. You know, we are still working on many things in the world to, okay, they are unhappy. Okay, the impact of convection on the large scale, we'll talk about it in other lectures. It's just an equation. So I'll just conclude here. I think we've tried to describe three things. We've tried to describe the convective instability. Right? In simple terms, you can try to refine it by adding complexity. What is creating the convective instability? We've tried to talk about convective entities and then the convective parameterizations. But this was just an introduction, so thank you very much for your patience.
I hope it's audible. Yeah, thank you for that interesting talk. My question is about the slide number 64, where you had shown, I think from the model parameterization, yeah. So we see here the updraft is in a very small fractional area as compared to the subsidence portion. So any insights into like what in the natural system makes the updraft to kind of get on a really smaller fraction area, and it it's adjusted or redistributed by the subsidence on a larger area? Why not 50-50? It's a very small area. So any thoughts about it? We've been hearing about it like since so many years, like that is what we observe in the nature, but do we have a plausible explanation for that kind of thing which we observe in the nature? So that's one question. Thank you.
I think it's a nice philosophical question, and it's probably difficult to answer in simple words, but I'll try to bring some elements of answer to that question. So first, a parameterization approach on your question. So I think when people built these mass flux parameterizations, you know, it's a long time ago, at that time, the grid boxes were huge, like hundreds of kilometers, many degrees, a couple of degrees, I should say. And the time step was quite large. So if you look at such a big box, then you don't expect to have clouds everywhere. You know, some places will not be cloudy. Actually, most of the places will not be cloudy. So this approximation is fairly valid if you have a big grid box, and if you're looking at 1 hour time step, something like that. So this is actually just because at that time it was fair to make that approximation. We still carry these assumptions now, which is more problematic because they might not be as true as they used to be. So yeah, that's why your question is getting increasingly relevant, because now we still assume that in many cases, but we cannot always do that. A second approach on your question is that convection, as I defined it, it has to be a sort of a rapid motion, right? The timescale of that vertical motion of air is relatively fast. And so if it was 50-50, it means they will all be the same speed. So I would not even be wanting to call this convection. Yeah, we could debate, maybe okay, convection, but it would not be, you know, what we usually think about convection as being something approximately faster than just the natural overturning of air. And the third approach towards your question is that when you have many processes building convective instability in the system, this convectivity is usually built up, but there's a resistance against just releasing it like this. And this resistance is the SIN, the convective inhibition that we saw in, you know, the QT-LOCP diagrams. This convective inhibition is just forbidding any air that's, oh yeah, I'm unstable conditionally, to just go over that energy barrier and just start to, convect. So you have this barrier that you have to overcome. And because of that, it's just not any air that is unstable that can be released by convection. It has to be a pocket that would first manage to break the SIN through just release convection. So I think because of this barrier, I think this has to be relatively small. It has to be somewhere, but finally it breaks the instability. Otherwise, you would not have any instability. It would always be stable because it will always be 50-50, always be stable. So I think it's because of that.
So is that even valid for dry convection? Here we speak about moist convection.
Yeah, that's
so
right.
what's the case with dry convection?
Yeah, it's a very good point. It comes back to the definition. I'm saying this is a model of convection, but it's a model of moist convection, you're right. So usually when people want to describe the dry convection, they have a boundary layer parameterization, which is not a convective parameterization. So that's right. I think, you know, again, if you just want to describe convection, we think about them being interlinked, but to model this, we separate just to make it tractable. So this dry convection is going to be dealt with by just the boundary layer or the turbulence parameterization. So, yeah.
Hello, sir. Nice presentation, sir. Like in recent studies, most of the studies talking about tropospheric temperatures warming.
Sorry?
Tropospheric temperatures are increasing. If tropospheric temperatures will increase, how those impact on the cloud formation and development stages? If it is true, how to implement the which type of characteristics we have to change in parameter schemes in models?
I think it's a good question. So the question is, how do we modify the parameterization so that they are valid in a context of climate change where it might be warming? So first of all, the basic idea is that what creates convection is the convective instability. This is always going to be true, independently from climate change. So the question is then, what is the stability? This stability might be changing with climate change. So if your parameterization is not modeling that change of the stable profile, like in the adjustment parameterization, you know, this old school of thought, then yes, it could be a problem. You would have to adjust this reference profile to take into account climate change. But as long as your parameterization is just dealing with instability, I think you should be able to manage this. In practice, this was the theory. In practice, there's many parameters in a convective parameterization, and these things can be tuned on the current world, not necessarily taking into account the climate change. This is not what I'm talking about here, but in practice, I think it is indeed difficult because there's many parameters and you cannot really control exactly how they change. That's why when you have a parameter in the model, you want it to be as basic as possible, so it doesn't change with whatever, you know, like we have the Planck constant before. This is not going to change with time. This is good, but of course we cannot do that. But we try to make this constant as basic as possible. Yes, you have to be very careful.